So thank you, organizers, Michael, Vipin, Laura, everybody. And so I'm Ansu Chatterjee from the School of Statistics here at the University of Minnesota. And that was a set of 5 brilliant talks up to now. And my talk is slightly different. So what you heard from the previous speakers were very, very interesting applications, very, very interesting forays into using science for building better machines, using machine learning for better understanding of science. And so that there was a lot of development on the interplay between science and machine learning. I'm going to go a little bit deeper into the foundations of it. Why does that happen? Why did the system of equations that Laura showed just now, just a little while back, why did it work? Why did a deep learning model actually work? So here's a lot of maybes. This is a theoretical work. Also, as a theoretical work, I should have had a lot of equations, and I've sort of deliberately tried not to have equations out here. I know you lose half of your audience with every equation. So, so before I get there, let me just up front, I'm part of a different HDR grant, Harnessing the Data Revolution grant. I'd like to acknowledge that, along with other grants from the divisions of mathematical sciences and DMR. So you could learn more of our projects from these links. And as I was saying, this talk is mostly an overview. I'm not going to present new results, essentially. And this talk includes work from a lot of different groups. And what I'm going to do is we're going to explore the different ways deep learning, in particular deep neural networks, DNNs, relate to things that would allow you to do uncertainty quantification, that would allow you to discover equations, as Laura was doing, that would allow you to combine different varieties of doing machine learning, or like the way Arindam, Anuj, Vipin, everybody else was doing. So, and here's a bit of a shameless plugin to begin with. If you are affiliated with the University of Minnesota, there's a class that I'm teaching next semester, beginning in just a few more days, Statistics 8931, which is on the foundations of data science, which would have way more details than what I can present in 15-20 minutes on essentially exploring the connections between machine learning, AI, and other fields of data science. All right, so let's jump in. What exactly do we know about deep neural networks, and why do we bother? Why would we want to study a link between deep neural networks and, for the purpose of this talk, Gaussian processes? You could already see from the work Arindam presented, Laura presented, that there are connections, there are things that you could just build into the algorithms. So deep neural networks have certain fantastic performance demonstrated in tasks that are essentially discriminative. I mean, it can do great in distinguishing cats from dogs, or in being able to say where a boundary of two blobs of different colors lie, and things like that. So that's what deep neural networks are really good at in many contexts. It's essentially also a black box. So why are we here? We are here because just being able to say this is a picture of a cat as opposed to that being a picture of a tomato is not really sufficient. We are here, this whole thing Vipin and his group has organized is because we would like to leverage that in order to do science. And we'd like to use science in order to help us build better algorithms. What we are aiming for here is interpretable deep neural networks. So in order that deep neural networks are useful for doing science, we need to be able to understand what exactly is happening inside that particular black box that we're building. So that's the purpose of this workshop. That's the purpose of a lot of this harnessing the data revolution HDR grants have been working on. And so here's a bit of an entry into that world. So in order to get there, in order to help us understand what's happening inside a deep neural network, we need to be able to relate that to the scientific method. We need to understand what kind of features is it picking up, or upweighing or downweighing. Also, this is something that Arindam brought up, and then Laura, of course, brought up. We should be able to do more science, understand more than what we had put into the deep neural network about. So that relates to being able to test a scientific hypothesis, being able to frame new hypotheses, and very, very, very critically for doing any science, not just the ones that were presented, but everything, whatever we do with deep neural networks needs to be reproducible. Now, all of these goals would be met if we could actually associate a probabilistic framework with deep neural networks. And that's the reason why looking at the connections between deep neural networks and probabilistic systems, and I'm just illustrating things with the most prominent one that's out there, Gaussian processes. That's why we study that. All right, let's see. Okay. So part of what we know is that, did I move a slide? All right. Is that all right. Yeah, so what do we know about deep neural networks or artificial neural networks in general? Now, something that has been known for a very long time, for decades now, is that if you take a shallow network, a two-layer network, so basically meaning only one hidden layer, and make it infinitely wide as you would like it to be, you could pretty much approximate any continuous function with arbitrary degrees of precision using that particular neural network. So that has been known for a while. And this is a deep field of research. People have been showing that you could do the same thing with a long, narrow network. So arbitrary depth, but each hidden layer in a neural network is narrow, it's bounded. And here's a typical result. And I actually, if I click there, I'm jumping in. So by the way, anytime I present a theorem or something like that here, I'm not stating all the conditions. So don't jump at me for that. So let's say you have got a probability distribution sitting on so a discrete probability distribution sitting on like 2 to the power n points. You could train a deep belief network, which is not particularly popular these days, but it is another kind of a artificial neural network with about 2 to the power n minus 1 depths. That could get arbitrarily close to this. Okay, so a deep but narrow network does work. It also does not require more parameters than what a shallow, wide network would do. So these are the kind of theoretical results that have been developing. And some of these are coming out even now. One got published, a really good one got published last month. So what is this universal approximation theorem that artificial neural networks do apparently satisfy? At least some of them do. So it's kind of a baseline thing, something that in a statistics or in a probability community sort of corresponds to being asymptotically consistent. If you cannot do it, you're doing something wrong. So that's the first step. But this particular angle, universal approximability, does not actually tell us anything about either the interpretability, rate of approximation, uncertainty quantification, and stuff like that. So what else do we know about shallow wide networks? And this is something that Radford Neal, who's actually a very, very brilliant person, contributed tons to this field, came up with in his thesis, that if you take this two-layer network infinitely wide, what you're pretty much doing is you're doing stuff that a Gaussian process would do. So there is a connection between the shallow wide network and Gaussian process. So that's the other connection through which we actually get into a probabilistic framework. So I know there are hundreds of people in the audience, and many of them are students. So let me just do a quick one-slide introduction of what a Gaussian process is. It could be defined over any domain. Think of time as an example, but pick your favorite domain. You could pick any Euclidean space. You could pick any manifold, anything. The big deal is that you should be able to define a positive definite function over there, meaning that anytime you construct matrices of this sort, that should be a positive definite matrix. If you are able to do that, and your stochastic process is such that pick any dimension, pick any set of points that has a multivariate normal distribution, a Gaussian distribution, you have a Gaussian process. So deep neural networks relate to this object. So again, just to recapitulate, deep neural networks have excellent discriminative performance. We know that they're scalable. Wonderful algorithms have been developed. There are some limitations. GPs, on the other hand, they can do the probabilistic tasks. They're suitable for hypothesis testing, getting confidence bounds, prediction intervals, and stuff like that. They are typically not scalable. Choosing that kernel, choosing this function, that k function on the previous slide, is actually a hard thing. So building a deep learning and a GP connection is actually something that could be pretty cool. It could combine strengths from both of these worlds. Bring in scalability with all the stuff that you'd actually need to make deep learning usable for science. It couples with what I've started calling the United Sciences of Data. You bring in all the data science streams together as you do this sort of stuff. So it's a wonderful world for me. Okay, there are actually many, many, many ways of linking deep neural networks with Gaussian processes. I've listed a bunch of them. I mean, you could read these slides later on, so I'll not really go over every single one of them, but I'll go over 3 really interesting cases. But the whole idea is that you could relate deep neural networks with Gaussian processes in many different ways. I'd point out to dropouts here. Everybody loves a dropout. It became the Irengal thesis, and its subsequent usage is now incredibly popular in the community. That is another way of relating deep neural networks with Gaussian processes. So here's the first of the 3 different ways in which you could tie in neural networks with Gaussian processes. And so that long list that I had on the previous slide, most of them were about relating the architecture of deep neural networks, the structure of a deep neural network, and relating that to Gaussian processes. This one is different. This one relates the training method, the training algorithm. So Arindam mentioned some time back, one of the standard techniques of training any neural network or any such complicated data science machinery, like even a lasso these days, is to go through a gradient descent, typically a stochastic gradient descent. So you look at your cost function and then try to go towards at least a minima or an accumulation point at least of that and hope that that's the global minima kind of a thing. So that's how gradient descent works. You could do a slightly different variant of a gradient descent called a kernel gradient descent. This sort of leverages how the network has been built. And that gives rise to something known as a neural tangent kernel. So this neural tangent kernel seems to stabilize if the width of your deep neural network tends to infinity. And this actually is a kernel relating to a particular Gaussian process. This is actually a different way of kind of relating deep neural networks with Gaussian processes, and it's something that we've been working on, and we are finding fantastic properties out of this. So here's an example, and I should mention these are all other people's works. Mostly, we've been reproducing some of it, but so let's say we have a supervised learning task, and here's the boundary that separates the two classes, the blues from the oranges on my screen. So this boundary is something that a deep learning methodology would actually find out for you. What a Gaussian process does is sort of gives you an equation for this line. Now just think back at what Laura was saying. This is about discovering equations. What this neural tangent kernel-based Gaussian process is also able to do is say that there's a lot of uncertainty about A or D, which are close to the boundary. Our confidence in saying B is blue or E is red is much higher. So far less uncertainty. That's how one of these things go. Here's a second DL-GP connection. This is known as NNGP, neural network Gaussian process. We construct a fully connected multilayered perceptron, so your usual feed-forward network with random weights, biases. And then you move the whole thing through, except that you compute at the last layer, at the output layer, a kernel that corresponds to that. And then instead of using your stochastic gradient descent, you take that kernel learning and treat the output layer as a Gaussian process. Okay? That actually outperforms doing standard deep neural networks on here's some very standard data sets where it does very well. In all these cases, you'll see that the neural network GP actually does better, sometimes significantly better than the other ones. So this is, again, not our calculation. So the table is actually from a paper that reported this, but we've been able to reproduce this more or less entirely. Here's the third variety. So fully connected multilayered perceptrons, the feed-forward networks are interesting, but people really use convolutional neural networks, LSTMs, and things like that. So where does Gaussian process sit in that perspective? Well, so here's what happens. So this is a bit more challenging. We have a low-dimensional parameter, essentially, in a CNN, instead of having too many parameters to work with. So some of the techniques of relating deep neural networks to Gaussian processes do not work. The other problem that comes up is that calculating that kernel, that all-important kernel function, becomes incredibly hard. Also, when you're going to a realistic world, going to an infinite width or an infinitely deep neural network is a very unrealistic scenario. So here's something that has happened recently, and again, this we found a ton of interesting details here. Newer results I'm sort of postponing to our next workshop on this sort of stuff. So this is an idea due to Rasmussen and his team. And what I've presented here is a major oversimplification, but you essentially play with the position of the kernel filters as well as the filter values to a situation where it turns out that you could ignore tons of covariances, and the kernel recursions themselves become really, really simple. So there has been recent discoveries that relate convolutional neural networks to Gaussian processes. And so there's a ton of challenge. I mean, we know this. We've been able to get to that point with CNNs. RNNs are still an open problem. And here's something that, again, on MNIST dataset relates what a CNNGP is able to do compared to something that I showed you just moments back, NNGP. Now, this, you might say, improving on a decimal place here and there is not really a big deal. That's entirely true. I mean, this is not just about prediction, not just all about this last column where you show that you've improved on a second or a third decimal place. What these GP variants are able to do is that they're also able to tell you, give uncertainty bounds. So essentially say that this is significantly better than that one, and so on. Okay? So they are able to do uncertainty quantification at that level, which again is great. They are able to pick up the correct sort of features. So associate the kind of the univariate distribution, sort of like the ones that Laura showed you for those weights with her model. So something like that for every weight or sequence out here. Just to wrap up stuff, I see Michael has come on screen, so it's probably time for me. Again, just acknowledging all the grants, and thank you. I've got a bunch of references here for those of you who need to see the slides. So,
okay. Thank you, Ansu. We do have a question. Many atmospheric processes are non-Gaussian and quite skewed. Is there an approach we can use with those sorts of systems?
Yeah, totally. So this is partially what I meant by saying that this is mostly an overview. This is a relationship that I'm showing you between deep learning and Gaussian processes. However, you could go to, this also relates to a question that was asked during Laura's presentation. You could go to extremes. You could go to skewed distributions. You could go to things that are built. So there are other stochastic processes that you could relate to. I would especially mention two that we are working with. One is what I call a randomly scaled Gaussian process, and the other one is what's traditionally known as an elliptical process. These are things that you could also relate to. So the GP, the Gaussian process, comes from a limiting argument. If you go into more terms and not just the limit, so the limit plus the next order term kind of a thing, you would be able to capture the skewness part of it and so on. So this beautiful mathematics and machine learning relationship that actually happens out there. So yes, certainly it can be done. It is being done.
Good. Thank you, Ansu. I'd like to thank all the speakers in this session for the